Hi, Matthew. I think yes, Supreet. I think Matthew has joined.
Hi Venkatesh. Hi Supreet. Hi team.
Hello, Matthew. Thank you so much for sparing your valuable time and
Yeah.
addressing the contributors here. Uh, Great to have a session with you. Supreet, over to you for introducing Matthew, and then we can take up the session forward.
Yeah.
Sure.
Okay, great. Thanks for joining in today, Matthew. Great to see you. And I know you've been participating in a lot of the discussions with the C4GT cohort for your products. But great to have you here. Look forward to hear from you. Everybody, we are joined with Matthew. He is a technology architect, system designer, and a polyglot programmer at Taranto. Taranto is an organization that is building digital public goods and also deploying them for different government use cases, including Karmyogi Bharat. He has over 18 years of experience in architecting and developing enterprise applications and scalable platforms and mobile applications. I'm really excited to have Matthew here because Matthew is one person who's actually not just designed things, but has built them and has also seen the implementation of them in real life scenarios. And I think for all of us, we experience different aspects of building, designing DPGs, but to hear from somebody who's seen the entire life cycle and has had a lot of learnings as well. I've had the opportunity to work with Matthew on a few items, but all of them have been sticky enough to say that there is so many learnings and challenges that you have to navigate. So Matthew is full of that experience. So I'm going to give it over to Matthew, who's going to share a little bit about different Sunbird blocks and will tell you a little bit about his experience in designing and implementing some of these as well. Matthew, great to have you. And just for context, we are joined by all the people who've been selected in the C4GT program. And this is part of the 4-day bootcamp. Today is day 3. Tomorrow is the last day and followed by the inauguration event. And then we'll start the coding period on 1st July.
Sure. Yeah. So thank you for inviting me to this session. And I'm really happy to see the kind of response that the program has got overall. And I must say that it was a very tough choice to choose the best contributor from amongst many competing, really well-written proposals. But yeah, and I would like to use this opportunity to talk about Sunbird. So I've been associated with building Sunbird for the last almost 6+ years now. And I have a PPT, so maybe I'll just share my screen and we'll run through. Okay, let me know if my screen is visible. Is my screen visible?
Yes.
Yeah.
Okay, cool. So I'll start by talking about, building blocks. So when you set out to build a digital public good, you know that you are trying to solve some challenge at a country scale. And you probably don't know all the kind of requirements or considering the diverse nature of various countries, I mean, India particularly, you do not have a very pointed perspective on how a certain platform should evolve. So it is important when you build such platforms, when you attempt to build such platforms, you should adopt a building blocks thinking. And what do we mean by a building blocks thinking? We mean that you should try and build as many modular components as possible. So some sort of a Lego architecture is what you should think about. And why Lego architecture? Because you may have to pivot your technology needs midway, or maybe as you progress through your platform's journey, building journey, you might realize that certain components that you thought were valuable were not so much valuable, or maybe they were ahead of time. And you may have to quickly pivot your technology thinking. And for that to be done efficiently, it is important that we adopt a Lego architecture. So when we say Lego, we are looking at minimalistic components which can be composed to create the larger solution. And of course, because we are building a digital public good, you have to assume that whoever is going to run the platform or run it as a digital public infrastructure is going to need a fair bit of configurability as well. Because that's the only way that they can really tailor the modules that you have written or the components that you have written for their use cases. And any scalable system that you build, it has to be data-driven and automation-focused. You need to have the ability to observe how are users engaging with your system, how are your microservices or your technology components interacting with the hardware that they're running on. So you need all sorts of observability. And of course, when there are too many moving parts, automation is key, because you want to avoid human errors, and you want to ensure that everything is repeatable as well, by not just whoever is building it, but by the adopters of that digital public good. And if you want to really allow innovation to happen on top of what you've already built, of course, innovation can happen at multiple levels, but being API driven is definitely one way to do it. Ensuring that you have APIs which are reusable by people who are trying to solve similar problems, and also allowing people to actually build on top of your APIs. So that's equally important as well. We have taken all these good principles, and we have applied all of that while building Sunbird. What is Sunbird? Sunbird is a set of building blocks which can power population scale applications. Okay. And I don't want to run through all the Sunbird components, but I want to focus on Sunbird Ed, which is a full-fledged learning platform solution. And Sunbird Ed internally uses some of the other Sunbird building blocks to accomplish. Like when you think of a learning management solution, you need to be able to represent content. You need to be able to represent the user interactions with the content and all of that. So that's where all the other building blocks are used. And each of these blocks has been built keeping in mind that they can have alternate use cases from just being used in assembling a learning management platform as well. So there's a fair bit of configurability and domain agnostic capability built into some of these building blocks. Okay. And talking about Sunbird Ed, the largest adoption of Sunbird Ed is Diksha. Diksha is a national learning platform for students and teachers. And if you look at the numbers, you can see that, till date, I mean, this is measured from 2019 or 2020. So we've powered, 500 crore plus learning sessions, about 6,000 crore plus minutes of learning, and many number of page hits as well. Right. And if you look at the kind of now Diksha being so Diksha is powered by Sunbird Ed. The Sunbird Ed is the software part, which is the digital public good. And Diksha is the implementation of Sunbird Ed, which makes it the digital public infrastructure, right? And Diksha, because it is using open standards and accessible to all, it does not enforce a login. So we have about 30 million anonymous users. And about 15 million registered users. So if you have to take things like courses on the platform, you have to be a registered user. It's probably one of the rare government apps which has a 4+ rating on the Play Store with about 35 million installs. And talking about the scale, there have been days where we have seen 40 million content plays on a single day. And because we focus a lot on observability, and we focus on a lot of events being generated when users and the software interacts with the hardware, we have seen a billion and a half plus telemetry events. Telemetry is the JSON structure that we I'll talk about it maybe in a later slide. And we've seen about 25,000 transactions per second at peak. And while all of this was happening, we were sending out about 4 petabytes of data, from the data center, because it is a content delivery platform. About talking about the textbooks, there are around 4,500 plus textbooks which were printed with QR codes. So when I say 4,500 plus textbooks, I'm referring to the various boards in the country, multiplied by the number of subjects and the grades that they are applicable for. But in essence, around 60 to 70 crore physical textbooks were printed with these QR codes, and there are about 2 lakh plus content pieces which are live on the platform. Okay, moving on. How did we build a platform that can scale so well? So these are some of our platform design principles. we were very clear that if we have to scale out to India scale, we have to rely on some of these design principles to kind of allow the system to scale as and when the demand arrives. So we chose a non-blocking tech stack, which is also resilient by design. Everything that we have built in Sunbird, and thereby Diksha gets it as well, has to be horizontally scalable. Vertical scaling does not work beyond a certain point, so that's a definite no-no. You have to have an event-driven design thinking. I will, share a bit more of the event-driven design in a later slide. Of course, it's not just about the application. You have to be able to deploy the application on a cloud that is equally elastic, right? When you're talking about 25,000 transactions per second, you need load balancers, you need sort of machines that can handle that kind of scale. You also need the capability to and 4 petabyte, 5 petabytes of monthly data going out, so you need that sort of network capacity. So you have to be able to deploy on the hyperscalers and yet be agnostic. That's important, because you don't want to have a lock-in with one cloud and then figure out that the digital public good is only compatible with one cloud. That's not a good situation to be in. Security is again paramount. You start with perimeter security, leveraging API gateways, and you would slowly realize that API gateways can only do things like basic role-based access control. If you want fine-grained security and policies, you would have to have additional layers coming in, and I'll talk about that in a later slide as well. And observability. So you need to know how your platform, how your infra and the usage metrics, so business metrics and the infra metrics, both of them add to the observability. Now I want to take a deep dive into each of these blocks. So we'll look at non-blocking microservices. So I spoke about how you want microservices, all your code to be non-blocking. And there are many ways to write non-blocking code. I mean, in Java, you have frameworks like Webflux or Play framework, which allow you to write non-blocking code, and stacks like Node.js are inherently non-blocking, but we chose that we would go the Java way, or Java plus Scala way. So we have used Play framework, which internally uses Akka. Akka is a slightly different paradigm than writing, for writing concurrent applications. So we've used a combination of Play framework with Akka to create microservices which are non-blocking. And when I say non-blocking, what it means is essentially these microservices, while they are invoking other services or interacting with the data stores, you don't want a thread to be blocked, right? That's what it means. And for any async processing, we have actually been using Kafka pipelines, and we use Flink Jobs, which is a streaming platform. So the way you can visualize the streaming platform is that you can have publishers producing events into your pipeline, and streaming jobs can take an action as and when an event arrives. And some of these frameworks are truly scalable. Now, if you create microservices which are non-blocking, and you have taken care of the best practices, you also as and when and you can scale out the microservices as load increases, right? You can put them into auto scaling groups and things like that. When you do that, it is important that the underlying databases also scale, and for that we have for various needs we have chosen these databases that you can see on screen. So for our content model, we use Neo4j, which is a graph database. And for our data pipeline and observability stack, we've used Kafka. And if you look at the reference scale of some of these as well alongside, Neo4j is really scalable. It can store billions of vertices. And we ourselves have benchmarked it for about 2 million vertices and 40 million relations across these vertices. Kafka, again, it's a LinkedIn, LinkedIn open source Kafka years ago. And at LinkedIn, they have clusters which process 1 trillion messages a day, right? And we have been able to leverage Kafka with a much smaller cluster to process about 200 million messages an hour, which translates to about, slightly about 2 billion messages a day, right? For all our search needs, we use Elasticsearch. We have benchmarked it with 1 billion documents and sub-second response times at concurrency. And Cassandra is something that is very dear to us, because we realized that if you use a SQL database, you are pretty much always on one master and multiple read replicas. And if you have one master, you have some physical limits on the number of database writes that you can do, because you can only do writes to a master. You cannot do writes to the slaves, but reads can go to the slaves. So there are physical limits on how many writes per second you can do, and our targets were way beyond that. So we chose Cassandra, which is a multi-master database. And of course, there is no silver bullet here. I mean, if Cassandra gives you a multi-master capability, it also means that you have to know how to leverage Cassandra and use the best practices. There are capabilities that you get right out of the box in the SQL databases, which are not available in Cassandra. But it allows, there are certain best practices, and you kind of need to learn to model data on Cassandra, the Cassandra way, right? And for all our analytics, we use Druid. Druid is being used at Netflix. It's a very, very scalable analytics OLAP store. We have our Druid clusters ingesting millions of events every hour on a 10-node cluster. Okay, so that's kind of a view of the data store choices that we've made in Sunbird. And what you see here is basically from our benchmarking results. And what we have done is the scripts that we use for benchmarking is also open source as part of Sunbird, which you can find in this GitHub location. Okay. Moving on. So observability. Now, I spoke about how it is very important to have an event-based architecture, event-based design, and observability is key as well. So this stack that we have here, and Lambda architecture is an industry standard in data engineering. You basically have two layers. There is a speed layer and a batch layer. The speed layer is going to be real-time ingesting data. So every interaction that your users have with your systems, the easiest way to visualize that is, let's say that you have built, you're building a mobile app or you're building a portal. You could define events like start events when a user logs in or a user starts a session. And you could have like impression events when, the users move across screens, and maybe interact events when they interact with widgets on your screen, right? All of these events, you can visualize events as just JSON envelopes, basically with some attributes. And what you try to capture in an event is who did what and why, right? So some contextual information. So, and that is the kind of information that you will ingest into a pipeline like Kafka. And then you will use any stream processing. So we've used Flink in Sunbird. There are other stream processing engines as well. And you would then try to process the data and then ingest that data into your data store, which is Druid, so that you can query. And the advantage you get is, because you are getting all these raw events, you can do queries like how many users have visited this particular page of my portal in the last 1 hour. Those kind of queries become very easy. But the fact that every user moving across pages is generating an event, which means the volume of data is also huge. And you cannot keep such huge volumes of data for a long time, because then, the cost becomes really high. So it is important to have a batch layer, which is summarizing this raw data. So an example of that is, assume that a user has come into your platform and played a content and it generated, let's say 100 events. You could have the summarization layer summarize all of this into one event and say that, a user came in, spent 10 minutes on the platform and visited these, 20 different pages, right? And that's the kind of summary data. And because you've summarized the data from like 100 events to one event, obviously, it's going to be easier to keep the summary events for a longer duration, and it's a bit more cost effective, right? So that's how the Lambda architecture works. And systems like Druid can scale out horizontally. You can literally keep adding more machines and they'll just keep scaling out, and you can ingest billions of events daily. So there was a point of time when our Druid clusters in Diksha had 100+ billion events, and it would still give us sub-second query times on that data. Okay. You also want to back up this data, these events into cloud storage, because it could also happen that, you at some point you also want to do maybe some past data analysis or something. So you need a source of data. So you will keep that in, your data lake, which is just cloud storage, and it's a bit more cost efficient than storing it on a database or a pipeline, queuing pipeline. So this is a standard data architecture. Are there any questions so far?
Hello, sir. I'm having a question.
Yeah.
Yeah. So, is this built on Java or Scala?
So we use a combination of both. Some of our microservices use Java, and Play framework is compatible with both.
So basically, like my project, like on a proposal stage, it asked me that for Java/Scala for backend.
Yeah.
So I'm a Scala developer. So
Right.
I chose Scala. So would there be any issue with that, or?
No, unlikely. I think you should talk to your mentor specifically on the project need, but if it is a Java/Scala need, I think that should be fine. Scala should be acceptable.
Okay, sir. Okay, sir. Thank you.
Hello, sir. My name is Premsay Verma. So, sir, actually, previous in this slide, like you showed the platform design principles, right? So, in that, please can you explain the term horizontal scalable and the opposite one, that is vertical scalable, like with some real life example.
Right.
Yeah.
Right. So let me take the example of a database. Okay. Let's say you are running a MySQL server. Okay. Now, there are various ways to deploy a MySQL. You can deploy a MySQL server, in a cluster where you have one master and multiple slaves. And you can configure it to say that, when the master dies or is unavailable, one of the slaves can get promoted as a master. So there are ways to configure this. But at any point of time, you can actually have only one master server, and all your database writes have to go to the master node, which means that the total number of writes that you can do, even though you have a cluster of database servers, is the maximum number of writes that you can do to that one master node, right? So what do you do if you want more writes? If you were on a, let's say, a 8 CPU, 16 GB RAM database machine, you will scale it up to maybe a 16 core 32 GB RAM machine. This is called vertical scaling, right? And SQLs traditionally only support vertical scaling because they support a lot of asset properties which are not possible if you do distributed computing. Not very easy to do when you do distributed computing. Whereas if you look at a database like Cassandra, every node that you have in the cluster is storing part of the data. So it is like a sharded data store. And what that means is, if you want more writes, you just have to add more nodes, right? And of course, there are a lot of trade-offs. So you have to kind of play around with the Cassandra data model and fine-tune it accordingly. So Cassandra, you can say, is horizontally scalable because you can add more nodes and it will scale out. Whereas, SQL databases are typically vertically scalable, which means you have to increase the size of the same machine because all the writes have to happen to the same machine.
Yes, sir. Thank you, sir.
Okay, so I'll move on. And I spoke about when you build such platforms, you have to ensure that these platforms can run on hyperscaler clouds. But it is also important that the solution is cloud agnostic. What I mean by that is, let's say you built a DPG, and I'll take the example of Diksha. Diksha was initially on Microsoft Azure, right? And at some point, they wanted to move it to a different cloud. And that was possible because while the solution would work on Azure, leveraging the best practices on Azure, it should also be possible with very minimal changes to migrate it into any other cloud as well, right? So, and what this slide shows is what are some of those techniques. Now, if you're a programmer, you can actually look at interfacing out calls to some of the cloud specific services. For example, most of the applications right now will have some sort of dependency on cloud storage. Now, if you're on Amazon, it could be an S3 bucket. If you're on Azure, it could be an Azure blob. Or if you have your custom data center, it could be a Ceph, an OpenStack Ceph storage gateway or something like that. Now, when you're writing source, at some point should allow somebody to configure it to be able to run in AWS or in Azure or on your custom stack, you have to have some layer of abstraction. So, what we have done is we have actually created an SDK, and that SDK is configurable, and the SDK underlying it uses Apache JCloud, which enables a lot of these features. So that SDK, you can configure the SDK to say that, you are right now working with Amazon S3 or Azure Blob. And from the application standpoint, they only interface with the SDK, and for them, it becomes cloud agnostic. So this is one of the techniques in which you build cloud agnostic applications while also leveraging the power of and scale of these cloud storage services, right? The other example, which is on the right side, is specifically about provisioning. Now, provisioning refers to the step where you actually take a VM or you take some cloud resource and you are able to install the necessary software to get that ready for, like, installing a database, for example, is one example of provisioning, right? Now, you will have to use some sort of automation for this, and while you're automating, you have to assume that the VMs may be on any one of the clouds. So you can use open source tools like Ansible to create automation scripts which are cloud independent, because but they will be operating system dependent, but they're still cloud independent. So if you have a Ubuntu VM on Amazon versus an Ubuntu VM on GCP or Azure, or your on-prem, Ansible will work seamlessly. So these are two examples of how you apply cloud agnostic thinking when you start building these kind of systems. Okay. Moving on, security. Now, security is a ever evolving subject. You typically, now, if you look at this, you will have your clients which are making TLS connections to a load balancer. And you would typically have a reverse proxy, which handles routing of your requests and many more things. Reverse proxies are very powerful. You can do things like caching the most frequently accessed APIs. You could do things like restricting the request from a particular geography and things like that. So you will typically hit a reverse proxy, and you will start with using an API gateway. An API gateway will ensure that some basic form of role-based access control can be enforced in an API gateway. But if you want more finer, security, you will have to really look at using some sort of overlay policy engine like OPA. OPA stands for Open Policy Agent. It's getting very popular, and OPA allows you to in a very descriptive way describe what are the kind of checks that you want to do, with the user context, the API request body, and only then allow the user to access your endpoint. So an example of this would be, let's say that you have admin role for a particular tenant on the system. And while making the API call, you're actually passing the tenant ID of a different tenant, and you want to block things like that. Those kind of things can be done leveraging layers like OPA. Okay. And when you set up these many hops in infrastructure, you need observability. You need to understand how many API calls are coming to your API gateway. You need to see how many of them are responding with 200 HTTP 200s, how many of them are getting rejected with security tokens missing, how many of them are getting timed out. You need all that kind of visibility. So in Sunbird, while leveraging API gateways and reverse proxies, we have also put in the kind of metrics, metrics collectors, which can actually collect these kind of metrics. So there are metrics collectors like StatsD, and also certain Prometheus exporters, which can collect these kind of metrics from these kind of components and get all that data into a centralized Prometheus. And you can then paint nice graphs, which allows your team to understand how many calls are happening, what is the average response time of the calls, and many more things. right? So, and API gateways can also do rate limiting. So if you, for example, if you want to limit, a single user from making only 10 calls per minute against a particular API, those are things that you can configure in the API gateway as well. So all these components have to be working together and well integrated for you to have a very secure microservices architecture. Okay. Moving on, observability. When we talk about observability, there's the business metrics observability, which is about how many users are coming to your platform, how are they engaging with your platform, all sorts of funnel analysis that you want to do. All that is business metrics. You also want to observe, what is happening on your system, what's happening on your infra, right? And you also want to be able to have all your logs collected into a central place, because in microservices, typically, your request comes into one microservice, and maybe that microservice will call another microservice. So when you have, too many distributed systems interacting with each other, you need to be able to collect logs from all these systems and allow developers to access the logs in one centralized dashboard or something. And that's why the log aggregation part is important. So in Sunbird, we've actually used FluentBit, which is a log collector. So if you have VMs or Kubernetes nodes, you will have FluentBit running there, which is essentially collecting all the logs being generated by services running on that virtual machine. And that is going to ship it to, an Elasticsearch like log aggregation stack. Okay. And you will use a Kibana like front end to query the data that is in Elasticsearch. These node exporters and various, there are node exporters is one kind of exporter that Prometheus supports. If you run a node exporter, the node exporter exposes an API which can be queried by Prometheus. So Prometheus works in a pull model. I mean, it can also work in a push model, but the most of the Prometheus adopters leverage the pull model, which means you will configure Prometheus to query these node exporters at a certain frequency and collect the metrics. So node exporter would, return metrics like what's the CPU usage, what's the memory usage, what's the disk IOPS, and those kind of metrics about, from the nodes where they are running. And so all that monitoring data comes into Prometheus, and you can visualize that data using a dashboarding engine like Grafana, or you can, and you can also have alert manager where you can configure alerts based on data coming into Prometheus. So for example, if you want to do things like raise an alert if the average response time of this API goes from 10 milliseconds to 20 milliseconds, or if it goes about 20 milliseconds, those are the kind of rules that you can specify in the alert manager. All of these components that you're seeing or you've seen till now are open source, and you can leverage all these best practices in your applications as well. And you can actually see a lot of this in action if you look at the Sunbird repositories and go through the Sunbird documentation as well. Okay. So that brings us to the end of the presentation. These are a bunch of things I wanted to share with all of you. I'm happy to take questions now.
Hey, Matthew, thanks for sharing this, this details, overview of the different blocks. One thing as we get into questions would be great if you can shed a light on is, in your experience, what have you seen when you were implementing products? Let's say, for example, when you were implementing Diksha, for example, right?
Yep.
In any of these places where, you assumed something, but something else was the reality, and then, there was a gap. And then if you can just do that and make this real,
right.
And you'll have a lot of instances. Yeah.
So I can quote a couple of examples. Okay. So I spoke about how Cassandra is a very scalable database, right? But there is a way, there are certain best practices that you have to use while modeling data on Cassandra, right? And of course, we as a team did not get it right first time. So there are certain queries, if you run certain types of queries against Cassandra, Cassandra will allow you to do that, but it actually can bring down your cluster. And we had such queries. So there were a few night outs where we had to figure out that, there was a badly written query, which was just bringing down the entire cluster and impacting user traffic. So we've had, that is one example where, and this happens quite a bit in modern application development, because you use a lot of tech stacks. I mean, there is no, gone are those days where you have like just a Node.js and a Java layer and a single database, right? You're typically polyglot. You will be using multiple languages, multiple microservice frameworks, and multiple data stores. So it is important that you kind of get a sense of the best practices in that and you productionize it, right? That's one part. Second part is, while Cassandra was horizontally scalable, we were a bit scared to go beyond 3 nodes because, production, we thought 3 nodes is decent and our scale needs were being met. But during COVID time, when we started hitting millions of active users and all that, we used to see some patterns where these nodes had enough spare CPU and enough spare memory, but the queries were slowing down. And then we figured out that it was because the disk IOPS was maxing. And then Cassandra being such a well-designed system, while production traffic was underway, we could just add more nodes and it just self-balanced the cluster and it helped resolve. But these are things that we realized only once the traffic hit us, right? And one more example I want to quote is, I spoke about how you can have reverse proxies and API gateways, right, to kind of perimeter protect your microservices. Now, the first time we set these up, we did not realize that the default configuration on some of these were to use HTTP 1.0, and HTTP 2 is itself getting popular, and the most popular one at that time was 1.1. And if you don't use HTTP 1.1, you cannot use keep alive connections. Now, I just want to take a minute to explain what is a keep alive connection. Now, let's say that you have an API gateway which is making a call to your microservice. If you don't use keep alive, for every HTTP request that you have to fire from the API gateway to your service, or any HTTP call that has to happen between a client and a server, it will create a new TCP connection and then tunnel the HTTP data, get a response back, and then close the TCP connection, right? Now, when you are getting API calls at 1,000 calls a second, it means that for every call, you're creating a new TCP connection and then closing it. So you're having too many short-lived TCP connections. And this is so much stress on CPU. So what we figured out through our benchmarking is that if we are able to enable keep alive connections, and keep alive connections are only possible if you're using HTTP 1.1, which is just a configuration in a file, you can literally, on that same TCP connection, you can channelize multiple HTTP calls. And we figured out that you could save up to 10% of CPU on your API gateway. And I'm talking like, when you have 25,000 TPS, you have probably, 24 CPUs just manning your API gateway. So you could literally reduce 3 CPUs just by enabling this small feature. And all you need to do is, just enable it in a configuration, right? So these are some examples where we realize the hard way that, even while you use some of these tech stacks, which are really scalable, you really need to, there's that art of productionizing it, where some of these best practices come to light only when, the rubber hits the road.
Thanks, Matthew. That was a great, two insights that you shared. In fact, if maybe at some point later for the community, if you can, maybe share some links, because I know that, when people try to, we've been having discussion the past 2 days where different people have asked questions with regard to how can they design a DPG, what is it that you call a DPG, and then how can they, design something like it. And then Ravi had given an input saying that, look for the smallest problem statement, just do it well. And then can provide some more perspective around like, how to think about it from a practical use case. Will be great, because I know you've also driven a lot of design reviews. Like, for example, there is somebody proposes that I want to make a change. And then there is this entire design council that Sunbird has that reviews the, the design and provides inputs. And that's a very valuable way of thinking, which a lot of times you miss because you're not thinking scale. So if you can, point the community towards certain PRs that were raised, which got very good design feedback, that everybody can learn from, I think that will also be great, because that will make it also real for them to sort of experience, feedback. Sure,
Supreet. I can definitely dig out some good examples, although I want to assume that, broadly we have gone into that mindset in Sunbird that, most of the latest PRs will be taking care of all these concerns that we've discussed, but I can certainly find some good examples. Yeah.
Awesome. Great. Okay, everybody, any questions, thoughts, based on what you've heard? I think Shlok has asked one question also
Yeah,
on.
I see that. Does Neo4j also utilize for the ontology management? Yes. So Neo4j is a graph database. And by the way, graph databases are not really meant for transactional workloads. So while they scale in volumes, they don't really scale well for transactions per second. So any sort of graph database can be used to model ontologies because you essentially want to store vertices and linkages between them, right? So in Sunbird, Neo4j is used for by the Sunbird knowledge building block, which is storing the ontology graph.
Hello,
Yeah.
sir.
So any resources to catch up on the topics mentioned? Yes. Yeah, that's quite a bit of information there. So we have a YouTube channel for Sunbird, so you could follow some of the videos there. We have we have detailed sessions on how, let's say, Sunbird content management works, how the assessment engine works. So we have gone into details of many of these. But honestly, if you are building DPGs, I would say you can get started on reading about whatever databases that you use, right, and stacks that you use. Just rely on some of the design principles that I spoke about and get started with there. And the good thing in today's tech world is some of the best practices can be overlays. Some of them can be afterthoughts as well. It is really you can really improve things incrementally. So I would say get started. I would say read page 30 of the manual so that you get into the fine print of what are the best practices, how do you really scale out those components that you're using, and that's the best way to get started. And if you need more info on Sunbird, you can visit sunbird.org, and you can also search on Sunbird videos on YouTube, and you should get access to a lot more material.
I think Shlok had something more to add. Shlok, do you want to share something that you were raising,
Yes,
and then
sir.
we put that?
Yeah, hello, Matthew sir, Shlok
Right.
this side. So, sir, my question was like, we are utilizing the Neo4j, and you are also mentioned that there are millions of vertices in the
Yeah.
Neo4j for the
Yeah.
ontologies management.
Yeah.
So, like, first question is like, where we are utilizing the ontologies? Are we doing some link analysis, or what are the processes through we are utilizing the graph database? And the second question is, like, how we are managing, because sir, I have previously worked on Neo4j, and the part that I have been figuring out that there is the management of the vertices and the relations that we have to maintain. So like when we are doing with that much data in which we are creating the millions of relationships and millions of vertices, so like what are the key points and how we will do that, so that's what my second question.
Sure. So I'll tackle the first one. Your first question was, do we do some sort of analysis of the linkages and things like that? So the reason why we envisioned, it as a knowledge management system and not a content management system is because we wanted to do recommendations. Okay. So there are many experimental tracks that we have done. We have also tried taking some of them live, but with lesser success, I would say. So the entire idea of patterns, it becomes possible because you have these linkages, right? So the only advantage, or one of the big advantages of linkages, is because of linked data, you can inference more about the data, right? Now on to your second question. I mentioned that Neo4j is probably not scalable for a transactional workload. Okay, so what we have done in Sunbird is whatever it's only the creation of content or the updation of content, only the metadata gets stored into Neo4j, and for that we have actually written a graph engine. Okay, so Neo4j is not very efficient when it comes to doing certain things like merge queries and things like that. If you get into the details, it's not very efficient. So we created our own application layer to handle some of those things, right? Because sometimes what is best for you rather than relying on a database capability. Okay. And to scale out the read capability of this metadata, what we also do is, for every update that happens in Neo4j, we also generate events, and we have a streaming job which actually uses these events to populate data into an Elasticsearch cluster. So, all the consumption or all the user searches, or if a user says, give me content for grade 1, this subject, which is covering this topic, that does not go into Neo4j. If you send that to Neo4j, your Neo4j will stop working, right? So we channelize that into Elasticsearch. So that is how we kind of, we get the benefit of the linked data, but we also get the scale of Elasticsearch, and we rely on Elasticsearch for serving user needs. And sometimes you even go to the extent of caching this in a Redis, like, frequently accessed content. So if you look at a platform like this, it could be that some state has asked all its teachers to take a particular course on the platform, right? Now, the moment such a need comes up, you will have suddenly 5 lakh teachers coming searching for the same course. So you would benefit from caching a lot of that, because you don't want to channelize all these queries even to your Elasticsearch, because there's a cost there as well. So you might end up caching some of that data in Redis, so that frequently accessed data can be put into Redis and leveraged.
So like that you have mentioned, if we haven't taken example of the I Got Karmyogi platform, that there's the architecture also. So like in which we are using the ontologies for the recommendation system, that like if particular user has the particular videos interest, and the particular user have also the particular, so those linkage between the data, like whether it is mostly it is a text data that is related to the, if this person is interested in this, if this person is also interested. So are the recommendation based on the Neo4j that is utilized?
Yes, but that is still experimental.
Okay.
Yeah, it'll take some significant usage, especially on the iGot platform, because it's hardly 1 million plus users only. In Diksha, we have tried recommendations, but again, the effectiveness, so I would say that, it's a ever evolving thing. Yeah. Good question though. Yeah.
Thank you, sir.
Yeah. Okay, so there's a question from Manas. Right. So Manas, if you can be a bit more pointed with your question, you mentioned half of, half the things mentioned, you probably did not connect with what problems you're solving. So maybe if you can be more pointed in your question, I can try answering it.
Manas, maybe you can turn your camera and share. Yeah.
Yeah, so what I was referring to was that you're using a lot of tools, right? Like in the API gateway, Nginx server, and a couple of pods for that. Those, I understand what those do, but for most of the other things you're talking about, it was kind of went through my head. I don't know why they're there. It feels simple that you just need a database. You just need a connecting server to just connect them. So why are they for?
Right. So I think when I was attempting the Neo4j question, right, I think I've tried to answer. So maybe I'll connect the dots there, right? So we wanted to store content and linkages between content. So now when you look at the content, right, I mean, you will have assets, you will have content linkages to a taxonomy and all of that, right? So we wanted to store that data in a graph. Now we chose a graph engine for that, right? And once you choose a graph engine, now you know that you want millions of users to come in and be able to query that data. And graphs are not really meant for querying at population scale, right? So you need some mechanism to take the data in the graph and put it in a data store, which is more efficient and more specialized for search. So that is Elasticsearch. Okay. And so that's so are you clear now? So you have Neo4j for storing, linked data, and you have Elasticsearch where the same data is actually put as JSONs so that you can query them and searching. I mean, Elasticsearch is specifically meant for searching. So that's the reason for using Elasticsearch. And Cassandra is used for all sort of transactional data. For example, imagine this. Now you've created a content, you've allowed a use, and somebody has created a course, which is like a series of contents that you can play. And somebody wants to store what's the user's progress on a content, right? So you want to be able to say that a user has enrolled into this course, and this course has 10 content pieces, and he has actually played 5 of them, right? And this is the time spent. So that kind of data, you can neither store them in Neo4j or Elasticsearch. So you have to choose a better database for that, and that's Cassandra.
Got it. Okay.
And all these databases, they are predominantly online transaction processing stores. I mean, barring Elasticsearch, which is mostly a search engine. So you also need to have the ability to query data, for your analytics, and that's where Druid comes in. So Druid is something. So you can visualize Druid as a MySQL on steroids. All sorts of SQL queries can be run, but you can, you can aggregate data based on any columns and things like that, right? So these days, platform development is about choosing the right tool for the job, the specialized tool for the job, and knowing how to leverage the best practices so that it just scales.
Got it. Yeah.
Hello, sir.
Yeah.
I'm having one.
Yeah.
So I have regularly observed this, that while we are, doing some big data processing, and like if we are making a huge amount of data travel in some data pipeline or something, we are often using like Cassandra only. And I have seen this like at a lot of places, including the Sunbird that you have gave an example. But as you explained, if our motive is to use NoSQL only, why we are not using the popular ones like MongoDB?
So in our data store, right? See, MongoDB is still a single master store, Siddharth. Okay, and we for our data stack, right? We want to be able to use a horizontally scalable solution where each cluster member owns a certain volume of data, and you're not restricted to doing writes only to one particular master in a cluster, right? So that is very limiting. If you have a 10-node cluster, and if only one of the machines can take writes, and when you look at data analytics use cases, a lot of events will get generated and they have to be ingested, right? So you want all the 10 nodes to be able to handle, or maybe 5 of the nodes which are designated as ingestion nodes to be able to handle the ingestion, right? MongoDB like databases are not really popular at doing that. And so you have to use specialized data stores like Druid or Pinot or ClickHouse, or, I mean, there are various commercial offerings as well, but you should look at a more specialized data store.
Okay, so like at one place, like MongoDB is still used.
Yeah, so if your scale is low, MongoDB works as well. A few million events, MongoDB works. In fact, when we started Sunbird, we did not use Druid. We were actually storing, some of our analytics data in Elasticsearch itself. But the moment you have more than 1 billion events to query, Elasticsearch we felt was a bit more on the costlier side. So we decided to choose a specialized tool for it, and we shifted to Druid.
Okay, thank you.
Okay, I think those are the questions. Are there anybody else with questions? This is great. Thanks so much, Matthew, for taking out time. I don't think there are any more questions at the moment. But yeah, I think there's a lot to absorb also from the session. And I'm sure that as people start implementing some of the solutions that they're planning to, they'll have more thoughts. What we're doing, or the team is doing, is that they're summarizing whatever they're discussing through the day. And also what you're sharing with them as part of, like, we've created a group on Discord where it's being shared so that people can go through it, and then what we're trying to also do is to make some constructs very clear. Like yesterday, one thing that was coming out was difference between personally identifiable information versus aggregate anonymized information, right? Which is emitted from DPGs. I think that is such a familiar construct that we forget that, not everybody is so accustomed to it. And that's why that concern about how data is going. So any construct also, Matthew, that you feel that the team, should learn immediately, do let us know. Aim is that over the next 2 months, everybody who's here can ramp up on some of these things also, and can comfortably handle discussions on these subjects independently in their micro communities, from wherever they're joining in. So yeah, but no, thank you so much for your time. Hope you also had a good, session from your side.
Yeah, it's good to see the kind of questions that are coming. I mean, really nice. Yeah.
Yeah, thank you so much, Matthew. Great having you, and look forward to continued engagement with you as we move forward in this program.
Yeah.